Amorphous silicon is the non-crystalline form of silicon used for solar cells and thin-film transistors in LCD displays, used as semiconductor material for AC solar cells, or thin-film silicon solar cells. It is deposited in thin films onto a variety of flexible substrates, such as glass, metal and plastic. Amorphous silicon cells generally feature low efficiency, but one of the most environmentally friendly photovoltaic technologies, since they do not use any toxic heavy metals such as cadmium or lead. As a second-generation thin-film solar cell technology, amorphous silicon was once expected to become a major contributor in the fast-growing worldwide photovoltaic market, but has since lost its significance due to strong competition from conventional crystalline silicon cells and other thin-film technologies such as cadmium telluride and CIGS. Amorphous silicon differs from other allotropic variations such as monocrystalline silicon of single crystal and polycrystalline silicon that consists of small grains, also known as crystallites. Description: silicon is a four-fold coordinated atom that is normally tetrahedrally bonded to four neighboring silicon atoms. In crystalline silicon, this tetrahedral structure continues over a large range, thus forming a well-ordered crystal lattice. In amorphous silicon, this long-range order is not present. Rather, the atoms form a continuous random network. Moreover, not all the atoms within amorphous silicon are four-fold coordinated. Due to the disordered nature of the material, some atoms have a dangling bond. Physically, these dangling bonds represent defects in the continuous random network and may cause anomalous electrical behavior. The material can be passivated by hydrogen, which bonds to the dangling bonds and can reduce the dangling bond density by several orders of magnitude. Hydrogenated amorphous silicon has a sufficiently low amount of defects to be used within devices such as solar photovoltaic cells, particularly in the protocrystalline growth regime. However, hydrogenation is associated with light-induced degradation of the material, termed the Stabler-Wronski effect. Amorphous silicon and carbon. Amorphous alloys of silicon and carbon are an interesting variant. Introduction of carbon atoms adds extra degrees of freedom for control of the properties of the material. The film could also be made transparent to visible light. Increasing concentrations of carbon in the alloy widen the electronic gap between conduction and valence bands. This can potentially increase the light efficiency of solar cells made with amorphous silicon carbide layers. On the other hand, the electronic properties as a semiconductor are adversely affected by the increasing content of carbon in the alloy, due to the increased disorder in the atomic network. Several studies are found in the scientific literature, mainly investigating the effects of deposition parameters on electronic quality, but practical applications of amorphous silicon carbide in commercial devices are still lacking. Properties. The density of amorphous C has been calculated as 4.90 times 1022 atom per cc at 300 K. This was done using thin strips of amorphous silicon. This density is 1.8 plus or minus 0.1% less dense than crystalline C at 300 K. Silicon is one of the few elements that expands upon cooling and has a lower density as a solid than as a liquid. Hydrogenated amorphous silicon. Unhydrogenated AC has a very high defect density, which leads to undesirable semiconductor properties such as poor photoconductivity and prevents doping, which is critical to engineering semiconductor properties. By introducing hydrogen during the fabrication of amorphous silicon, photoconductivity is significantly improved and doping is made possible. Hydrogenated hydrogenated amorphous silicon (CH) was first fabricated in 1969 by Chittick, Alexander and Sterling by deposition using a silane gas precursor. The resulting material showed a lower defect density and increased conductivity due to impurities. Interest in a CH came when Lecombe and Spear discovered the ability for substitutional doping of a CH using phosphenoldiborane. The role of hydrogen in reducing defects was verified by Paul's group at Harvard, who found a hydrogen concentration of about 10 atomic percent through IR vibration, which for CH bonds has a frequency of about 2000 cm-1. Starting in the 1970s, a CH was developed in solar cells by RCA, by which steadily climbed in efficiency to about 14% in 1989. Deposition processes. Applications. While a C suffers from lower electronic performance compared to CC, it is much more flexible in its applications. For example, a C layers can be made thinner than CC, which may produce savings on silicon material cost. One further advantage is that a C can be deposited at very low temperatures, e.g. as low as 75 degrees Celsius. This allows deposition on not only glass but plastic as well, making it a candidate for a roll-to-roll processing technique. Once deposited, a C can be doped in a fashion similar to CC, to form P-type or N-type layers and ultimately to form electronic devices. Another advantage is that a C can be deposited over large areas by PECVD. The design of the PECVD system has great impact on the production cost of such panel. Therefore, most equipment suppliers put the focus on the design of PECVD for higher throughput. That leads to lower manufacturing costs, particularly when the silane is recycled. Photovoltaic amorphous silicon has been used as a photovoltaic solar cell material for devices which require very little power, such as pocket calculators, because the lower performance compared to conventional crystalline silicon solar cells is more than offset by the simplified and lower cost of deposition onto a substrate. The first solar-powered calculators were already available in the late 1970s, such as the Royal Solar 1, Sharp L8026, and Teal Photon. More recently, improvements in a C construction techniques have made them more attractive for large-area solar cell use as well. Here, the low inherent efficiency is made up, at least partially, by the thinness. Higher efficiencies can be reached by stacking several thin film cells on top of each other, each one tuned to a quality-specific frequency of light. This approach is not applicable to CC cells, which are thick as a result of the construction technique and therefore largely opaque, blocking light from reaching other layers in a stack. The main advantage of a C in large-scale production is not efficiency, but cost. A C cells use only a fraction of the silicon needed for typical CC cells, and the cost of the silicon has historically been a significant contributor to cell cost. However, the higher costs of manufacture due to the multi-layer construction have, to date, made a C unattractive except in rolls where the thinness or flexibility are an advantage. Typically, amorphous silicon thin-film cells use a PIN structure. Typical panel structure includes front-side glass TCO, thin-film silicon, back contact, polyvinyl butyral and backside glass. Unisolar, a division of energy conversion devices, produced a version of flexible backings used in roll-on roofing products. However, the world's largest manufacturer of amorphous silicon photovoltaics had to file for bankruptcy in 2012, as it could not compete with the rapidly declining prices of conventional solar panels. Microcrystalline and micromorphous silicon. Microcrystalline silicon is amorphous silicon, but also contains small crystals. It absorbs a broader spectrum of light and is flexible. Microamorphous silicon module technology combines two different types of silicon, amorphous and microcrystalline silicon, in a top and a bottom photovoltaic cell. Sharp produces cells using this system in order to more efficiently capture blue light, increasing the efficiency of the cells during the time where there is no direct sunlight falling on them. Protocrystalline silicon is often used to optimize the open circuit voltage of AC photovoltaics. Large-scale production Sunlight Corporation, which has received over $40 million of institutional investments, has completed the installation of its first 25 megawatts wide web, roll-to-roll photovoltaic manufacturing equipment for the production of thin-film silicon PV modules. Anwell Technologies has also completed the installation of its first 40 megawatts AC thin-film solar panel manufacturing facility in Henan with its in-house designed multi-substrate multi-chamber PECVD equipment. Photovoltaic thermal hybrid solar collectors. Photovoltaic thermal hybrid solar collectors are systems that convert solar radiation into thermal and electrical energy. These systems combine a solar cell, which converts electromagnetic radiation into electricity, with a solar thermal collector, which captures the remaining energy and removes waste heat from the solar PV module. Solar cells suffer from a drop in efficiency with the rise in temperature due to increased resistance. Most such systems can be engineered to carry heat away from the solar cells, thereby cooling the cells and thus improving their efficiency by lowering resistance. Although this is an effective method, it causes the thermal component to underperform compared to a solar thermal collector. Recent research showed that a CHPV with low temperature coefficients allow the private to be operated at high temperatures, creating a more symbiotic private system and improving performance of the CHPV by about 10%. Thin film transistor liquid crystal display amorphous silicon has become the material of choice for the active layer in thin film transistors, which are most widely used in large area electronics applications, mainly for liquid crystal displays. Thin film transistor liquid crystal display show a similar circuit layout process to that of semiconductor products. However, rather than fabricating the transistors from silicon that is formed into a crystalline silicon wafer, they are made from a thin film of amorphous silicon that is deposited on a glass panel. The silicon layer for TFT LCDs is typically deposited using the PECVD process. Transistors take up only a small fraction of the area of each pixel, and the rest of the silicon film is etched away to allow light to easily pass through it. Polycrystalline silicon is sometimes used in displays requiring high TFT performance. Examples include small high-resolution displays such as those found in projectors of viewfinders. Amorphous silicon-based TFTs are by far the most common, due to the lower production cost, whereas polycrystalline silicon TFTs are more costly and much more difficult to produce.